Alright, so here's a classic problem. Using the Biot-Sovart law, find the magnetic field a distance a above an infinitely long wire carrying a current I. And then the professor or TA puts the Biot-Sovart law up on the board, and you're thinking, what the fuck does that even mean? That doesn't look like an integral I've seen a day in my life. There's a vector in here? How do you integrate vectors? No one taught me this shit, because no one did teach you it. It's actually something you learn at the end of Calc 3, and you're currently in Calc 3 right now. So I'm going to try and teach you the things that they didn't teach you yet, starting with parametrized curves, leading into line integrals, and then we'll actually solve the problem at hand. Parametric curves, what are they and how do they work? You're already familiar with the type of parametric curve, a scalar function. For example, if you take the function f of theta equal to sine theta, the function f of theta, in this case, is dependent on the variable theta. This variable is a parameter to that function. If you were to update theta, for example, between -5 to 5, the value of f of theta will change in accordance to the value of theta that you input into sine of theta. Now that's fine and good and all, but we're going to need to know how to do this in 3 dimensions. So let's take a look at this helix, for example, and figure out how to plot this. How do you plot this? The answer is with a vector valued function. If you look at this helix from the top down, you'll notice that it kind of just looks like a circle. And that's our very first clue for how to actually plot this with a vector. Now an expression for a circle that you may already be familiar with is x squared plus y squared equal to 1. This is a problem because this is based off of 2 variables. We want just 1. Now if you look closely, you may realize that this is similar to another expression you're already familiar with, namely our trig identity. If we say here that theta is the angle that our vector is going to make with the x-axis, then we can write a vector valued function based off of theta for a circle of radius 1. The answer is right here. R equal to sine theta in the I hat direction, or the x-axis, cosine theta in the j direction, or the y-axis. And we'll just vary theta between 0 and 2 pi. Now this makes sense because this is the distance formula on a Cartesian grid, and this is the magnitude of the vector, radius 1. And there we have our vector valued function based off of the parameter theta. Let's return to the graph of the helix that we're trying to parameterize. Notice that it doesn't just exist in the x and y plane, it also extends in the z direction from 0 to 10. Also, notice that it doesn't make just one circular loop, but 2. So we need to modify our vector valued function for a circle to incorporate this new behavior so that we can create a vector valued function for a helix. As a reminder, this is our parametric equation for a vector whose arrow tip traces out the perimeter of a circle once, hence theta being from 0 to 2 pi. Now our helix makes 2 circles in the xy plane. So let's update our bounds from 0 to 2 pi to 0 to 4 pi to reflect that. Now recall that there is a z component for our helix as well, so we should update our vector valued function to reflect that as well. For f of theta, it would be easier if it was just dependent on theta, on one parameter. So we'll say that f of theta is just theta, and since it extends from 0 to 10, we'll update our bounds from 0 to 10. Now to make sure that it still only completes 2 circles in the xy plane, we'll change our cosine and sine function for the x and y component so that as theta updates, it only makes 2 rotations. Pause here and convince yourself that this is true. In case numbers on the screen wasn't convincing enough, here's that vector actually tracing out the graph. Line integrals are simply integrals over parametric curves. They're also sometimes called path integrals because you are integrating over a specified path. Now, one thing that you can do with line integrals is find the length of your parametric curve. To understand how this is done, we're going to move to a 2-dimensional context so that we can better understand how this can be done in a 3D context. Let's imagine we have some generic function x of t that is a function of time. This function can represent the position of an object in space with respect to time. And let's say we're interested in the distance this object moves between two different times, t1 and t2. If we take the first derivative of x of t, we get its velocity. That's just by definition. If we wanted to then know the distance that this object moves, we can integrate the velocity function between two different times that we're interested in and get the displacement of that object. To see how this is applied to parametric curves, we're going to return to our example of the circle. Now, the parametric function for the circle, as a reminder, should be on the screen. And the bounds are going to be from 0 to 2 pi because we're only going to do one orbit around the circle because we're trying to find its perimeter. Now, we don't have a function with respect to time, but we do have a function with respect to theta, and we can treat theta as our time variable. If we take the first derivative, we don't get a velocity with respect to time, but we do get something that's like a velocity with respect to theta. After all, the first derivative of any function just shows you the rate of change with which that function changes with respect to that variable. Now, the derivative is shown here below, and now is a good time to actually visualize what that represents. Now remember, we're trying to find the perimeter around a circle of radius r. With the differential that we found earlier, as shown on the screen, that's not really going to be possible because a perimeter is a scalar and we have a vector. Now, we can perform a vector operation that gives us a scalar, namely the dot product. Just as a reminder, the dot product tells us how much one vector points in the direction of another vector. The result of a dot product is a scalar, which is what we want. And when we take the dot product of something with itself, we get the magnitude of that vector squared. With that in mind, we can now find the scalar form of our differential. We just take the dot product with itself, and then we take the square root of that, and now we have our differential dl. Now, putting everything together, we finally get an integral that we can solve, and we find that the perimeter of the circle is 2 pi times its radius r. Look at that. We knew that. Cool. Now that we have that long, extensive background covered, let's return to the question at hand, which is using the Biot-Sovart law, find the magnetic field at a distance a above an infinitely long wire carrying a current I. As a reminder, here is the Biot-Sovart law. And I want to start by defining different components of this equation. Here highlighted are the constants. And within these constants, we have the constant I, which represents the current running through our wire. Next, we have our differential dl, which is what tells us that this is going to be some form of line integral. The difference being that we're going to have a cross product rather than a dot product because magnetic fields always point perpendicular to the direction of the current. The next two variables are going to be this curly r and r squared, which are difficult to define by themselves, so we're going to need a visual because the way that we define these two variables is related to our parametrized curve dl. Here's a graphical representation of the problem we're trying to solve. The blue horizontal line is our infinitely long wire. Now, once we've parametrized the curve, we're going to take the derivative to find its infinitesimal dl. dl is going to slide across our infinitely long wire as we integrate, and on our figure here, we should see one of the many dl's we will have. Now, our vertical line here represents a vector pointing to our point of interest, a distance a above our infinitely long wire. As dl slides across the wire, the angle between a and our curly vector r, which is our diagonal line, will also change. Now, the curly vector r is a vector that points from wherever dl is to our point of interest, that is a distance a above our wire. Now, with that image in our heads, we'll try and go into more detail. The r hat vector in the Biot-Sovart law is the unit vector of the curly r vector, meaning it's the curly r vector divided by its magnitude. The magnitude is just the square root of that vector dotted with itself, which is equal to little r. Now, the curly r vector is defined as the vector pointing to our point of interest a minus our infinitesimal. And now we'll try and define our parameter so we can find the infinitesimal. Now, the problem states that it's an infinitely long wire. So we're just going to have the wire sit on the x-axis and go from negative infinity to infinity. So our parametric curve will just be L equal to x in the I direction with the bounds from negative infinity to infinity. Now, the differential is just found by taking the first derivative of x with respect to x. It's just dx in the I hat direction. So now that we've defined our parametric curve and its infinitesimal, we can now find our curly r vector, which, remember, is the vector pointing to our point of interest a minus our parametric curve. Now, I misspoke and said it's actually minus the infinitesimal. That was a mistake. The result should be on your screen now. It's actually negative x in the I hat direction plus a in the j hat direction. And so our hat, which is the unit vector of our curly r vector, will just be that value divided by its magnitude. Just as a reminder, the denominator here is r, the magnitude of the curly r vector. Now that we've defined all the terms in this equation, we can now finally solve the problem. Substituting what we found previously for dl as well as r hat and the little r squared, our integral turns into this. Now, to move this integral to a more solvable form, we'll have to solve that cross product. If you're unfamiliar with how to solve a cross product, 3 Blue 1 Brown has a great video on how to solve it. I'll also leave linked below a document that explains cross products and dot products. But for now, I'll just solve it for you, and you should know that the answer is a dx in the k hat direction, which transforms our integral to mu naught I over 4 pi integrated from negative infinity to infinity of a dx divided by x squared plus a squared quantity to the 3/2 in the k hat direction, which is an integral that don't nobody want to solve. So how do you solve this kind of integral? Some might have recognized that the way you solve this is with a trig substitution. Others might not know what a trig substitution is. Others still might know what a trig substitution is, but don't remember how to choose which one. So what I'm going to do is I'm going to show you a nifty little trick to determine which trig substitution is appropriate. First, look at our integral. Notice that there are only two terms, x and a. A is a constant while x is a variable. If we look at the graph on our left, notice that I have a specific angle labeled theta. One function that we can use to show the relationship between x and a is the tangent function. In this way, you can clearly see that tangent theta is the ratio of our position on the x-axis with the height a. So if we rearrange this, we should get that x is equal to a tangent theta. So then the differential is just a secant squared theta d theta. So now we can take this substitution and we can substitute it into our integral. And what we get is the following. Now, as for the bounds, if you look at a graph of the tangent function, you'll see that at negative pi over 2 and pi over 2, or negative 90 degrees and 90 degrees, the tangent function has a value of negative infinity and positive infinity. So then we just replace the bounds with negative pi over 2 and pi over 2. To simplify this integral even more, if we take another trig identity, sine squared plus cosine squared equal to 1, and we divide the entire equation by cosine squared theta, we get another trig identity, tangent squared theta plus 1 equal to secant squared theta, we have another useful trig identity to simplify this problem. Now the only thing to do next is to insert this trig identity into our integral and simplify from there. And look at that. We have a pretty simple integral to solve now. So here's the solution. And just for funsies, this is what it looks like across the entire wire, or at least a subsection of it. Now the reason why you typically are given this type of problem to solve is because they want you to extrapolate that if you are close enough to a straight wire, then you can basically treat it as an infinitely long wire, and you can just use this equation to figure out the magnetic field a certain distance away from it. In addition, if you know how to use the Biot-Sovart law, then you can calculate the magnetic field at specific points around other types of wires. Maybe later I'll do a video on a toroid, for example. But if you like this video or you found it useful, please try and like and subscribe. If you have some disposable income, maybe even send me a little subscription on Patreon, because this was hard to make. But with that, I'm out.